We've studied this equation, 10 e to the negative x plus x. Where does that equal 7? Well, it's a nonlinear equation, and it's of a form that cannot be solved by hand. We are going to develop a procedure that will let us solve this equation, at least to a high accuracy, without actually having to get an exact answer of x equals by manipulating the equation itself. Our first step is going to be to simplify this problem from a two-sided equation where there's two sides that are interesting to a single side equaling 0. And that's going to make drawing pictures a little easier because we're going to have a function equaling 0. If we give this left-hand side a name, we're now looking for solutions to some function equals 0, or the roots or the zeros of this function. If we try to draw this graph, we should be able to identify at least roughly where we might find a solution. For instance, looking at the x values between 0 and 4, if we grab our calculator and plug in the numbers, when x equals 0, we actually get 10 minus 7 is an exact 3. When we plug in 1, it's not going to be quite as nice. If we just round for the purposes of sketching, we're going to get a value of around negative 2.3, then minus 3.6, and minus 3.5, and then minus 2.8. If we sketch that out, put the scale here, we see that at the origin we have a nice point at 3, or x equals 0. Then we go negative. Then we go negative even further, about 3.6. And then we stay negative, and negative 2.8 would be about here. So with that, we can interpolate a little bit and even sketch out the graph like so. That is the graph of f of x, which is equal to 10 e to the negative x plus x minus 7. Now we're going to go back to the graph, but ask yourself, where could a solution be based on the points you plotted? And take a look at this question as well. What property of the function would we be using to find that region? Well, if we take a look at this function and we know what we're looking for, which is where does that function value or y value equal 0, we can see pretty clearly that somewhere between 0 and 1, we expect there to be a solution. It might be closer to this point, we don't know the exact shape, it might be closer to 1, but it's certainly going to be between 0 and 1. Now think about the properties that led us to find that region. Let's formalize that. So on the interval x equals 0 to 1 is where we expect to see that. Now what property to use to find the region in that solution? Do you think about that for a moment? Implicitly, based on the 2 points that we had, one here and one here, we relied on the fact that this function was continuous to make our argument. Because that function is continuous and we know it starts above y equals 0 and ends below and it's drawn by one line, we know at least one point it's going to cross as y equals 0. It has to cross that point somewhere between the start and the end of that interval. It might cross more times, that's unlikely with the formula, but it has to cross at least once because of that continuity. Here's a more detailed sketch of the graph, and we can see the 2 points we calculated as well as one in the middle at x equals 0.5. What we're going to do is say, well, it looks like this is really close to the point we want. In fact, we're probably looking for somewhere here, but 0.5 is our good guess as to the solution. If we plug in 0.5 here, we're almost going to get a 0. For maybe not obvious reasons, what we're going to do is compute the derivative of the function at x equals 0.5. And here's how that's going to work. F prime of x, we calculate just the way you'd expect, derivatives. We'd have 10. The derivative of the e to the negative x is e to the negative x times, from the chain rule, negative 1. And we get a plus 1 and a minus 0. More traditionally, we would write that as 1 minus 10 e to the negative x, just arranging the signs. If we evaluate that at 0.5, we get 1 minus 10 e to the minus 0.5, and that boils down to a value around negative 5.07. So what does that help us with? Well, here's a zoomed in version. Notice this last point here is at 0.5. That's our location. And we know at that point the slope is -5, so it's very steep and down, though we have to be careful with our axes here. In other words, if it's down by -5, then if we went over half a step this way, we'd go up half of the 5, so we'd go up 2.5, probably about here. If we were to draw the tangent line at that point, we would get this blue line here, with the real graph going presumably somewhere pretty close to that, like so. And what do we notice when we see that? Well, I don't know the green line's shape exactly. We have all the information, though, that we need to build this blue line. We've got every detail. We have the slope, we have the point, and what do you notice? Those both share a very close approximation to each other of their roots. They both have the same root to a high degree of precision. And why is that true? Well, because the straight line and the green line share a lot in common. They have the same value and the same point, and we're not taking that big a step. So all of those properties of tangent lines we talked about earlier, that the tangent line and the real graph are very good approximations to each other when you're close by, also mean other properties like where the straight line crosses the axis and where the green line crosses the axis will also be very similar. We're going to formalize that process in the next video into something we're going to call Newton's method, and it will let us obtain, especially with a couple of repeated applications, a very high accuracy estimate of the solution to that equation that we started with. It's a very powerful technique that can be applied when we don't have a way to solve equations by hand.